Okay, so the other kind of rationalizing the denominator that we're going to talk about has to do with when you have two square roots in the denominator. So it turns out the way to rationalize a denominator with two square roots is to multiply the top and the bottom by what's called the conjugate. So the conjugate is where you change just the middle sign. It's not the same thing as the opposite. If I was making the opposite, I would change all the signs. Okay? So if your denominator has two square roots, or, well, that's a good point. They wouldn't have to both be square roots. This also works with something like 2 plus the square root of 3. It has to have two terms. You want to multiply the numerator and the denominator by the conjugate of the denominator. So let's see how that works. And we'll go to the second example. So we already saw this one. Now we're looking at this one. So we have 8 over 4 plus the square root of 5. We want to rationalize the denominator. So what they were saying is to rationalize the denominator, I'm going to multiply the top and the bottom by 4 minus the square root of 5. Okay, so I'm going to go ahead and bring this up. So let's take this one step at a time. So I'm multiplying the top and the bottom by the conjugate. Just change that plus to a minus. So upstairs I have 8 times 4 minus the square root of 5. And downstairs I have 4 plus the square root of 5 times 4 minus the square root of 5. Now here comes the whole reason that you want to multiply by the conjugate on the top and bottom. This expression right here, 4 plus the square root of 5 times 4 minus the square root of 5, is what we call a difference of two squares. I get very excited whenever I see one of these. It has the form a plus b times a minus b. And whenever you multiply an a plus b times an a minus b, what you get is an a squared minus b squared, which is what you see here. Okay. What you could do is try foiling that. All right. If you're watching the video, you could even pause the video and try to foil this. You'll see that you get the same thing. Otherwise, hopefully you know about difference of two squares, and that's how they got this. Okay. So I haven't done anything upstairs. I'm just leaving that the way it is for right now. 4 squared is 16, and then the square of the square root of 5 is just 5, right? The square and the square root cancel each other out. So that's how I get rid of my radical in the denominator. 16 minus 5 is 11. And so now at the very end, I'm going to distribute the 8 on top. 8 times 4 is 32. 8 times minus square root of 5 is minus 8 square root of 5. So the equivalent form for this expression where the denominator is rationalized is 32 minus 8 root 5 all over 11. All right, so that brings us to principal nth roots. In the trigonometry class, I'm not super interested in getting really deep into nth roots. Really, the main thing I want to do is just make it so that when we get to rational exponents, that'll make more sense if we've reviewed what this means. Okay, so up here you see the definition. The nth root of a equals b means that b to the nth power equals a, and I have an example down here. So you could read this as the third root of 8, but most people say the cube root of 8. The cube root of 8 is 2, because 2 is the number that when you raise it to the third power, you get 8. All right? That's the idea behind an nth root. Okay? Now, it turns out that it's pretty important whether the index of the radical, and by the index, I'm talking about this little number here, is even or odd. Okay? If that index is even, then the number inside has to be non-negative, just like with a square root. All right, so square root would be an example of that. And then the number that comes out is also non-negative, and again, that's just like square roots. However, if the index is odd, then a and b could be negative. All right, that's okay. All right, this symbol is called a radical, and the expression under the radical is called the radicand. Okay. So let's see, what are we going to do with this? We are going to jump right into rational exponents. Okay. So if the nth root of a represents a real number and m over n is a positive rational number, then a to the power m over n means take the nth root of a and then put the answer to the m power. All right. You can also do it in the reverse order. You could do a to the m power first and then take the nth root. They will give you the same answer. Okay. All right. So up here they specified that the fraction m over n has to be positive. So now they're getting ready to talk about what does it mean, or what would it mean if that fraction was negative. Well, hopefully in another class, in an algebra class, you learned what negative exponents mean. Negative exponent means reciprocal. Okay, and fraction exponents are no exception to that. So if I go here, all right, a to the power negative m over n means the reciprocal of 1 over a to the m over n. So there is a lot of what I call alphabet soup going on here. All right, the people who say, I'm okay with math until you put the alphabet in there. They're hyperventilating right about now. So I always like to, not dwell on something like this, but go right to an example. So let's look at an example. Okay, I forgot to animate that. 27 to the power 4/3. So just remember that the top number in the fraction is the power. The bottom number is the root. So this is talking about the 4th power and the 3rd root, the cube root. Okay. And if you're calculating a number like this, it's usually much easier to do the root part first because you're making the number smaller before you make it bigger. Roots usually make numbers smaller, and powers usually make numbers bigger. Okay. So over here, they're showing you that 27 to the 4/3 means take the cube root and then 4th power it. All right, raise it to the 4th power. The cube root of 27 is 3, right? Because 3 is the number that you have to raise to the 3rd power to get 27. And then 3 to the 4th power is 81. All right, here's another example. Using properties of exponents, they want me to simplify 2x to the 4/3 times 5x to the 8/3. Okay. All right, so the way that this works, this is a situation where I often say, think of a simpler, happier time. Pretend for a second that this 4/3 was just a 4, and this 8/3 was just an 8. All right, so it was just 2x to the 4th times 5x to the 8th. So hopefully that's a problem that you did 100 times in your algebra class. You multiply the 2 and the 5, and then you add the exponents. So if this was a 4 and this was an 8, the answer would have a 12th power in it. It works the same way if the exponents are fractions. So I'm going to go 2 times 5 is 10. And then x to the 4/3 times x to the 8/3, I'm going to add the exponents. And they have rigged this problem so that it comes out to a nice answer. 4/3 plus 8/3 is 12/3. 12/3 simplifies to 4. Okay. So that comes out to 10x to the 4th.